Morning, guys, and welcome to the second part of week 9. We are dealing with unit 25 today. We dealt with all of the units up to 24 at this point, basically. Yes, granted, we went all the way to units 30s and 34, 35, all the way to basically some 47, 49 units. So we dealt with the solar system that was, and after we were basically changing gears toward the stars now, and we're going to start with the sun immediately, first thing when we meet next time in Monday. So at that point, we're going to start the stars, really. We still have the rest of November to deal with all of the stars and even part of December to finish the entire topic. Unit 25 is not part of exam 2, not part of midterm 2. Midterm 2 is a week from today, which is Wednesday, November 9th. And on that day, we will not have a live session. We will dedicate the entire day just to the exam. So starting from next week, we're going to start with the units from the 50s, basically from the sun. We're going to discuss the properties of the sun overall, how it looks like, and then its structure and the magnetic field, the sunspots on its surface, and so on and so forth. And then we will delve into basically the nuclear processes happening in the core of the sun and some general properties of the sun before we move on to the stars and start classifying them. But that happens after this week, basically starting from next week, and that is not part of exam 2. That is part of exam 3, midterm 3. Unit 25 also is not part of midterm 3. So unit 25 is actually, if you wish, it's although light, it still deals with light, but it deals with the Doppler effect, and the Doppler effect is a critical piece of let me see if I can have the lab from this class in here, from the other class. No, I'm going to get some numbers in here because we will have some ideas in here into how to measure the wavelengths and so on and so forth. So the Doppler effect really deals with the stars, trying to determine how far the stars are, okay, using the Doppler shift. This is the premise upon which the James Webb is built, actually. The James Webb looks at the radiation coming from the faraway galaxies, actually. That's part of its mission anyway. And see the light that is coming for them, analyze the spectrum of the light that is coming from them, and see it shifted all the way to the infrared in a region where we cannot even see it with the naked eye. Hubble telescope cannot see it. So here is a galaxy that is from the far edges of the universe, a long time ago, sent its light. And its light basically went through all of the materials that it has, and mainly hydrogen. That's the main component of the entire universe. And that light, because of the fact that the universe is expanding at tremendous speeds, gets shifted, red-shifted, that is, because both us and the galaxies that sent it are moving away from each other. So it's not just the galaxy that is moving away from us, we are moving away from it. But in fact, nobody is moving. Not our own galaxy, not the other galaxies. The space between these galaxies is stretching. So in this situation, the light that left this galaxy some 13 billion years ago has taken that much time, but in the same time, the space is stretching and the wavelength is stretching. So the wavelength is getting longer and longer, meaning it's moving towards the red. As a matter of fact, it's moved so fast that it passed the red. It's in the infrared. So we cannot see it. This is the same hydrogen. This is the same hydrogen that has the four typical lines or 5 typical lines that you see for the spectrum, including some in the violet, including some in the from the red all the way to the violet. So the entire range is there, but the entire wavelength is shifted all the way to a region that you can't see anymore. The James Webb sees that. So that is light that has been emitted by a source. That source is moving away, and we're moving away also. Both of us are receding from each other. but effectively receding from each other. I know the space between us is the one that is increasing. So the light is stretched. This is what is known as a Doppler effect. How much is stressed, how much it should be, and how much it is, the difference between these two is the shift in the wavelength. Divided by the actual wavelength, this gives me the relative shift. And then multiply that by the speed of light, that gives me how fast the universe is expanding. So this is in a nutshell what this whole discussion is leading to. Obviously, this is for the faraway galaxies. It works also for the spinning stars. So if you have a star that is going back and forth, and we happen to be here, at some point it's moving away, at some point it's moving towards us. So at times the light is shifted towards the red when it's moving away, and at sometimes the light is shifted toward the blue when it's moving towards us. So if I know this shift in frequency, I can determine how fast this star is spinning. Obviously, the star is spinning because there is something next to it that causes it to spin. So there is, both of them are spinning around the common center of mass, which is called the barycenter. So if I know how fast this one is spinning, I know actually how fast the planet is actually moving. And that is part of, actually, for those sitting in Astronomy 125, the lab version of this class, we're able to determine the mass of at least one of the famous stars, 51 Pegasi b, which was part of the lab that we did, and we determined how fast it's moving, we determined how far it is from the star, we determined its mass, and we were doing all kinds of wonderful stuff using just the Doppler shift. Obviously, in the lab, for those sitting in Astronomy 125, we didn't do the calculation for the Doppler shift. We relied on already the values of the velocity with which the star was spinning. And those values, they came from the Doppler shift. Some of them blue shifted, and some of them red shifted. Some of them were positive, if you guys remember. I know a lot of you are actually sitting in that class. And some of them are negative, meaning some of them are moving away, some of them are coming out. And then when you plotted the graph, you found a nice, or at least you were supposed to find a nice sine wave. I know with the hand drawing, some of you nobody can get it perfect, okay? No matter how much you try, you have to really get a good computer fitting software to get it that nice sine wave. But it's still, you were able to see the motion back and forth, all of it due to the Doppler effect. So what in the world is the Doppler effect? Let me share with you the notes. So it's useful not just for the faraway galaxies, it's useful also for the close by stars, and for also determining the exoplanets, like, for example, what we did in the lab, 51 Pegasi b. So let me find my notes. So again, the Doppler shift is a common phenomenon that you can experience, and I'm sure you did in your life, even if you don't remember it, okay? If you're sitting, driving, doing anything at all, and you hear the emergency vehicle, either an ambulance or police, fire truck, or a police have the siren on and they're moving, you could tell without looking whether the police officer or the fire truck or the ambulance is coming towards you or moving away from you, intuitively. You don't have to take this class. You don't have to take any class to understand that the car is coming to, is approaching or moving away, just by listening to the tone. If the frequency gets higher, that is the frequency. In this book, we use the Greek letter nu. So the frequency, in other words, because it's sound, we call it a pitch. So the pitch is getting higher. Then we know that the vehicle is approaching. Okay. If, on the other hand, the frequency is getting low, lower and lower, meaning the pitch is getting lower and lower, meaning the tone more like this. That's exactly what a low tone sounds. It's like it sounds like an elephant basically making that. Or versus, for example, a bird chirping. That is the higher tone, bird chirping versus an elephant basically, or somebody yawning, okay? So that is a lower pitch. Then you know that the vehicle is receding from you. Either you're moving away, or the vehicle is moving away, or the combination of both of you. You may be going toward the car, you may be going in this direction, and the emergency vehicle is moving this far. So you may be doing, let's say, for example, 20 miles per hour. And this emergency vehicle is doing 50 miles per hour. You're going to hear the same thing, although you're moving towards it. But the vehicle is moving faster than you are. So in this case, it results in a net separation of 30 miles per hour. Obviously, if you're moving in the opposite direction, you're going 20 miles per hour in the opposite direction as it is moving 50 miles in the opposite direction, the separation is getting higher and higher, I mean, bigger and bigger. So in this case, it's going to go toward even a lower tone than it is in here. This is the separation is 30 miles per hour. This separation is 70 miles per hour. Okay, so in this case, the tone in here would be a lot lower than in this case. Okay, and vice versa. If you're approaching the vehicle and it's approaching you, then the pitch is going to be even higher than if you are moving faster towards it. Let's say, for example, it's doing 50 miles per hour and you're doing 70 miles per hour. Then in this case, the distance separation is shrinking and the Doppler shift will go toward higher pitch. But in that case, it's less than if you were moving in the opposite direction, in which case the pitch is even going to be higher than what it is in the other one. So this is intuitively what the Doppler effect is for sound. It is true for all waves, especially for light. Okay. And the similar analogy, as I was saying earlier, with the star. So if we happen to be here on Earth looking at a star, as the star is rotating, at sometimes it's coming towards us, and at times it's moving away from us. This is equivalent to the emergency vehicle coming towards us. This is equivalent to the emergency vehicle moving away from us. The Doppler shift in this case will result in light, whereas the wavelengths are supposed to be in here. So this is the spectrum of a given element, let's say, for example, hydrogen. Instead, in this case, since I'm going to assume the blue is here and the red is here, so in this case, the picture would look like this. All of it moving toward the blue. So this line, instead of being here, has moved to this much. This line will be here, it's moved this much. This line instead of here is being moved this much. And this line instead of there moved this much. So the entire spectrum looked shifted toward the blue because the star is coming towards us. On the other hand, and here, that spectrum, so this light instead of being here, it's actually closer to the red. This light instead of being here is closer to the red. And this one is also closer to the red, and so on and so forth. It's the same characteristics of hydrogen, except that the entire light shifts. And for the case of a star that is spinning, we will see the spectrum move back and forth, back and forth, back and forth. How fast it's going to move moving back and forth depends on the star and its neighbor, the one that is causing it to spin. How far away from the spectrum is going to move, then again, depends on the mass of the other object. If it's a supermassive black hole, for example, or a star is spinning so much around it, well, then in this case, it's that mass that causes it to spin too. Okay, so this is basically in a nutshell what the Doppler effect is. Okay. So, and again, this is an experience, this is a daily experience you can experience all the time. This is, by the way, what police officers also use for speeders trying to catch how fast they're moving. Basically, you have a vehicle that is moving, and the officer has a gun, a radar gun, sends a signal, either an optical signal or a sonic signal, basically either ultrasonic waves, sound that you can hear, or optical waves. And as they bounce back, if the vehicle bounces back, if the vehicle stops still, it's not moving at all, and the officer is not moving at all, then the frequency, there is no shift in it. So this is the emitted frequency. So he knows what the frequency is supposed to be. When it bounces back, the device measures the frequency that comes back, or he knows what the wavelength is. And as the wavelength comes back, he knows what the wavelength is. He measured the wavelength as it comes back. The difference between the two wavelengths divided by the actual wavelength. If he's using sound, he has to multiply it by the speed of sound. If he is using light, he has to multiply it by the speed of light. Here is going to give you the relative velocity with which that vehicle is moving. In other words, the police officer could be actually moving also with the radar on. Could be moving either this way or the other way, it doesn't matter. So what this device can calculate for you is the relative velocity, that's all. That's an important concept in here. To go back into my analogy to the beginning with the star, we could be moving. The sun is moving, actually. The sun is moving and the star is moving. If the star is moving towards us, then obviously this effect is affected by the entire thing. The whole spectrum will be shifted from this current place to a different place, and then we will be shifting back and forth from that. If the star is moving away from us, the entire spectrum again is going to be shifted toward that value, and then it's going to oscillate around the new position. But if we are moving with the same speed, then in this case, the spectrum will stay in its place because there is no relative velocity, but there is another relative velocity of this rotation. So all the device can measure for you is the relative velocity, not the actual absolute velocity. Not the absolute velocity. That's all we care for, honestly. We care for the relative velocity. In other words, the galaxy is moving away from us, and we're moving away from that galaxy. So what the James Webb is actually measuring is the relative speed with which these two galaxies are moving away from each other. What we could do, since we're sitting in this galaxy and talking about the rest of the universe, we could assume that this is the center with which everything is moving away from. And in that case, that galaxy will be moving with a combined velocity of our own moving away and its own moving away. So it's going to be the total velocity, and that's the relative velocity. For somebody sitting on another galaxy looking at our own galaxy, basically they will do the same thing, but their reference point changes to their own galaxy. So they will see us moving away from that. So this is in a nutshell what this expression is finding. It's not finding the absolute velocity with respect to an independent reference frame. It's calculating it with respect to each other. It's relative to one another. Okay, so it's very important that the police officer is not really measuring your own speed, but your own speed versus his own speed. So the difference between the two velocities. Obviously, he knows how fast he's moving. His device actually can tell how fast he's moving, and he can find exactly what your speed is with respect to the ground. So if he's, for example, moving, let's say, for example, 50 miles per hour, and the speed limit is supposed to be 50 miles per hour, his device, if you are, so this is the speed limit. So this is the limit, how much it's supposed to be. And his device finds that your speed is actually 60 miles per hour. I'm sorry, your speed finds it's your 10 miles per hour. That's because it's going to find the relative velocity. So relative to him, it's 10 miles per hour. So he, in this case, if you're moving in the same direction, he will need to add the 10 to the 50, and he will tell you, hey, you're moving too fast. You're moving 10 miles above the speed limit, because the speed limit, the posted speed limit is 50. If the speed limit is 45 miles per hour, and he's already speeding at 50 miles per hour, probably trying to catch up with you, and he finds that the relative speed is 10 miles per hour. So in this case, your relative speed with respect to him is 10 miles per hour, and you are 15 miles above the speed limit. So that's basically how this device works. So it doesn't measure the absolute value. It doesn't measure the speed with respect to the road. It measures the speed through with respect to the radar gun. But if he's standing still on the radar gun, for example, with the radar gun, for example, on the side of the road, and he has his radar, then in that case, the relative speed is the actual speed with respect to the ground, because his speed with respect to the ground is 0. So this is what this thing is. So it doesn't measure the absolute speed, it measures the relative speed. And that's all you care for, honestly. You don't care for the absolute speed. So this is the Doppler shift, okay? And again, this is the same idea. How does this come about? Where did this expression, I mean, it's written symbolically in here with the delta lambda, by the way, delta always changes for the difference between one thing and the other. So it's lambda, the measured value, minus lambda as it's supposed to be, divided by lambda as it's supposed to be. So in other words, for example, if I take the spectrum of hydrogen and I'm looking at this specific line, I know its wavelength. Let's say, for example, its lambda naught is 656 nanometers. So this is how much it's supposed to be. And let's say, for example, I measure it and I find that 500 and, no, actually, sorry, this is supposed to be 600 because it's closer to the red. Let's say, for example, 665. So, and I measure it, I find that 667 nanometers. So what's the difference between 667 and 665? It's 2 nanometers. That's the difference. So this is what it's supposed to be. And I found it to be here by 2 nanometers more than what it should be. So that is what the delta lambda. So the delta lambda in this example, it's 2 nanometers. I have to divide this number by the lambda, and the lambda is 665. 665 nanometers. When I divide the nanometer by the nanometer, they cancel. So it's 2 divided by 665 times the speed of light, which is 300,000 kilometers per second. That's why this number is big. Okay, let's take this example in here and see how fast this is relatively moving just by 2 nanometers shift in frequency. I have the calculator open in here. I'm going to do 2 divided by 200 by 665. So I get 0.003 times 300,000, which is the speed of the light. And this is moving at a ridiculous speed of 900 kilometers per second. So this star, if in case it's a star, it's going at 900 kilometers per second. This must be a faraway galaxy, not probably 13 billion years from that it sent this light. Otherwise, the shift would be much, much bigger than this. But it's still 900 kilometers per second, 902 if you do the math, okay? Or how much was it, 902? Yeah, 902.25, okay? But 900 kilometers, 902, it's the same thing, very close from each other. So 900 kilometers per second. Obviously, this is not per hour. I have to multiply this by 3600 to get it by hour. So it's moving with a ridiculous speed, okay? So 3 times 9 is what, about 30. 3.6 times 9 is about 30,000 kilometers per hour. Still tremendous speed, okay? That's for a 2 nanometer shift, but it's moving away. Let's say, for example, instead of finding 667, we found it, for example, moving at 660 nanometers, okay, less than the 665. Obviously, the number in this case is going to be -5 because 660 minus 665 is -5 nanometers divided by 665 still nanometers. So the nanometer cancels the nanometer, and this is actually approaching fast to us from where we are, relatively speaking. So even if we are moving away, this is still moving faster towards us. So, and if we are moving towards it, and it's moving even slow, we're combining at a big speed. So multiply by 300,000, by the way, to get how fast this thing is moving. So let's just do this number and see how ridiculous this amount is. So again, we're gonna divide 5 by that number. Okay, let me do the math in here correctly. Okay, so I have 5 over 665, which is what, 0.007 times 300,000. So this is moving towards us with over 2,250 miles. I mean, kilometers per second. 2,250 kilometers per second. This is moving super fast. It's ridiculously fast. This is true. Obviously, this is just an example for how to do the calculation. Okay, the shift for stars is much, much lower than a nanometer. It's usually a fraction of a nanometer. And same thing in here. So that's when you multiply it by 300,000, it's still a small number. Okay. So how does this whole thing arise from? Where did this thing Doppler shift? Can we explain the Doppler shift? Here is the story. If I am here, and if I have a source in here, and the source is still, and I am still, both of us have velocity equal to 0. So what happened in this case, the source will send its light, let's say, for example, the red light for the hydrogen, and wait a whole period of time. Remember, the period is the inverse of the frequency, okay? So these lights are very, very, very high frequency, even if it's a red one. That means that the period is a very short instant in time. So, but I'm going to exaggerate this a little. So I'm going to say the next period is going to send another light, okay? And the next period is going to send another light, and the next period is going to send another light, and so on and so forth. So this is the first light that it sent. So this is the first one that it did. This is the second, and so on and so forth until we last to the one that is about to be sent, and so on and so forth. The source is still, we are still, there is no problem with it. We understand what's going on, and we have an intuition what that is, and we can see the color and it's it. Okay, no questions about it. The wavelength is separation between each two wavefronts. So this is a wavelength, this distance is a wavelength, this distance is also a wavelength. So every wavefront and the next wavefront, the separation between them is the actual wavelength. Here is the problem though. If the star, so I'm going to continue the analogy in here. So this is me. Let's keep me still in here. Let's say that we're not moving, okay? I know we're moving, but we care about in here is the relative speed. So the star sends its wavefront. This is the one that is going to arrive first to me. Sends it and moves. So it's not stationary. So when it's about to send the next wavefront, excuse me, the first one that I am about to see when the light first hit me has reached here. So this is the same first one that it sent from here because it's traveling with the speed of light. Remember, that's how I'm getting it. And that's how I got it in the first place, because the wave is traveling with the speed of light. So the source is about to send the second one. So this is the second wavefront now it's sent. Remember, the first has reached this point. The separation between, instead of being this whole separation, which is the whole wavelength, the wavelength now is only this. So the wavelength in actuality has shrunk because of the fact that the source is moving towards me. So the wavelength appears less. And if it's less, that means the frequency is higher. Remember, the frequency and the wavelength are related to one another through this relationship. So since the wavelength is shorter, the frequency must be getting higher. So that's when it's approaching me. When it's moving away from me, it's a different story. So here is the source. Here is me again. So the velocity is 0. Here is the source. It sent the first wavefront. It sends it, by the way, on a spherical shape. It sends it everywhere. So when the wave is left, it leaves on a sphere. Okay. So it starts the first wavefront. So here it is. So this is the first that I'm going to get first from when the light is. Then it moves away and is about to send the second one. So the first one would have traveled because of the speed of light here. So this is where the first one is. Now the source is here, actually. It says move to this point, and it's sending the second wavefront. So instead of sending it from where it was, had it been still, and the separation would be this much, the separation now is actually this much, is increased. Lambda is bigger now because the source moved away and sent the second wavefront. So since the wavelength now is getting higher, so this increased, the frequency must get lower so that the product is still 300,000 kilometers per second, always 300,000 kilometers per second. Wavelength times frequency is always equal to the speed of light. So in this case, I will see longer wavelength, meaning I'm moving toward the red. That is longer than the blue. Okay. In the first case, I'm moving toward the blue because the blue is shorter than the red. That's in a nutshell what it is. Now, if you happen to be exactly at 90 degrees, you're not going to see a shift because the source is neither approaching nor moving away. It's not, this separation is not shrinking, nor is it increasing. It's moving sideways. But if I am at any other direction, here or here, if I'm on this side, the source is moving this way. If I'm at any other angle, then there is a shift. There is a shrinkage in this case. There is toward the blue, but not as much as if I am head on. Same thing. If I am at an angle in this direction, any other angle other than 90 degrees, and not 0 degrees, or not 180 degrees, to be honest, because it's moving away, then in this case, I'm going to see a shift toward the red, but not as intense as if I am in here, not 0. So it's anywhere in between them. So in this example in here, you have a light bulb, and the light bulb is emitting in the yellow. The light bulb actually is yellow. If you happen to be in front of it and it's moving towards you, the light, instead of being yellow, it shifts toward the blue. It doesn't mean it's blue, really. It means that it's closer to the blue than its normal light source. But if you happen to be behind it, then in this case, you're not going to see it yellow. You're going to see it moving slightly toward the red. If you happen to be exactly at 90 degrees, you're not going to see that. You're going to see it yellow. If you happen to be at an angle in this position, anywhere in this position other than 0 or 90 degrees, then in this case, the frequency is going to move toward the blue, but not as much as had it been head on. The same thing with this one. So it's going to be probably green if it's at 45 degrees. Okay. And in this case, it's going to be orange, somewhere in between the yellow where it's supposed to be and the red where it could potentially be. Okay. So this is basically what the Doppler shift is. When we're looking at the star sometimes is moving as fast as possible towards us, but sometimes it actually has this component only towards us. So the shift in here is less than the shift in here. Sometimes it's moving away from us at full speed, and sometimes it's moving away from us at less speed than had it been on this position. And here it starts to shift toward the blue because of the fact that it's moving slightly closer to us. This is as fast. So it's this component that matters of that velocity. Here, it has no component moving towards us. It's moving sideways. So here, there will be no shift. Here, there will be no shift. So if I look at the spectrum in here of the different velocities after I use this formula, this velocity is going to be, the shift is going to be a negative value. So it's going to be, if I start from here, this cancels. This is going to be a maximum value moving away from us. And then this value will be 0. And this value is going to increase back to where it started from, and the whole process repeats. So we'll have a perfect sine wave projection of this motion. Looks close to a sine wave as possible. Okay. So this is in a nutshell how we use Doppler shift. Okay. Again, this is the same idea, that same point that I was driving to. If we are on this side on the Earth looking at this star, if it's spinning fast enough, then we should be able to see the shift. This portion of the star moving towards us, this portion of the star moving away from us. And this is actually used for the sun too. Okay, if it's moving fast enough, you could use it potentially. Depending on the broadening in here of this, depending on the delta lambda in here, you could see how fast this star is moving, how fast it's spinning. Okay, that's in a nutshell how this is. So V divided by nu, the Greek letter nu. Can I edit this quickly in here and enter an equation? What is the equation editor? Here it is. Okay. Oh man, I want to just write the Greek letter nu. No, sorry. Give me V, cancel. I want to just write the equation. Where is it? Insert? I'm sorry, here it is. That's what I'm supposed to do. And so that you guys know what the Greek letter look like, so it's not even in the basic math. That's mu, gamma. What is the Greek letters? And here is nu. Okay, so that's how it's supposed to be. Okay, so this formula is actually V over nu. Okay, so that's how it's supposed to look like. Let me delete these things now. So, oh, is it delta lambda over delta lambda? That's all. Actually, let's write this whole thing in a math format since we're doing this anyway. Delta lambda, oops, lambda, lowercase lambda equals V over nu. Okay, so that's basically what this whole thing means. Yeah, delta lambda is equal to V over nu, and V is the velocity over nu. And for the case of light, actually the velocity is C. So this is C over nu, where nu is the frequency here. Okay. So again, that's basically in a nutshell the formula that we're going to be using, and that's how we're going to find it. So again, for our problems, and this is the entire unit, so we're not going to spend more time on it. So delta lambda over lambda times the speed of light is equal to the relative velocity. It's a key important thing in here to understand that this is the relative velocity. Keep delta lambda in the same units as lambda. So if delta lambda is in nanometers, I mean, if lambda is in nanometer, keep delta lambda in nanometers so that nanometer cancels nanometer. Don't mix and match the units in here. Otherwise, this number is going to be a problem. And if that's the case, if it's the speed of light is always 300,000 kilometers per second. This is it. This is the entire unit. I really didn't want you guys to spend too much time, honestly, on it because we still have an exam that is due, and I really want you guys to focus on that exam. We'll be talking more about this Doppler shift when we get time to it, when we talk about the HR diagram, which is the Hertzsprung-Russell diagram, which is important for understanding how stars are classified and things like that. So we're going to get into a little bit more of that, but more so when we talk about galaxies and things of this nature. Check the chat. No, okay, no problem. Okay, thank you guys. And I will see you guys Monday, because we have a class on Monday. And then after that, we will not have a live class on Wednesday because we will be dedicated to the exam. Thank you guys. See you then. Okay,